All right, section 4.3, we're going to start talking about area. And in particular, this is going to be the area under a curve. So we're going to talk about the area of a plane region. So this is just a generic curve. There's nothing special about it. I'm just using the same curve on all my drawings, okay? And the idea of what we're going to be doing in the next, I think it's 3 sections of material, is we're going to find a way, or find different ways actually, they're related, but to find the area under this curve or between this curve and another location. In this case, we're going to be talking for the most part about the x-axis. So you're going to see a particular point given to you, so we'll call this point A and this point B. And what you're trying to do is you're trying to take and find the two-dimensional area right here that's trapped. That's our goal, is to find that area. And we're going to find eventually a very simple way to do it, but there is sort of a process by which we're going to come about that. And I'm going to show you today in this section a way to do this with rectangles, okay? And we're not going to get terribly complicated. You'll notice your homework doesn't have a ton of problems in this section, but I do want you to get a feel for how this process works, okay? So I'm going to erase this kind of shaded area that I just did in here, and I'm going to sort of draw in what we're going to be doing on the next different images. So we're going to be taking this region and we're going to be dividing it into smaller pieces. And in my example today, I'm going to be dividing this into 4 equal intervals. They're not always going to look quite equal, but just pretend that they are, okay? And we're going to turn this into, and draw, well, we're going to draw basically the vertical components of each of these. And the idea is that we're going to make a rectangle out of that shape. Now, clearly you can see that the base of the rectangles are very clearly defined, right? So whatever this length is right here, this would be one side length of the rectangle. The problem is that as I've drawn them in right now, there is no sort of height of the rectangle defined. In fact, you don't even really see a rectangle. You see just sort of a wedge, right? So there's 3 ways to determine the height, 3 basic ways. There are some other options as well, but we're going to focus on 3 basic ways to determine the height of a rectangle, okay? So the first way that we're going to look at that is by using left endpoints. All right, so what I'd like for you to do is I'd like for you to label this first point as x0. And the last point we're going to call it x4, and you'll see why in just a moment. And we're going to sort of subdivide this. So I'm going to cut it in half, and I'm going to cut it in half again. And please know that there's absolutely nothing special about the fact that I'm using 4 rectangles. We could use however many rectangles we wanted to. 4 is just easy to draw for the sake of argument right now, okay? And we're going to draw those vertical lines in that we drew just a minute ago at each of those places. They look more or less vertical, and they should look more or less evenly spaced. At least pretend that they are if they don't look like it, okay? So one way to talk about this is to take each of these sort of intervals and use the leftmost point as the height of the rectangle. So if we're looking at this first one, this particular point would be the height of this rectangle. We could draw a line straight over and then down from it, and this would be the rectangle. Clearly this overestimates the area a little bit, right? I've got a little bit extra going on up there. And I haven't done it yet, so let's do this now. We'll call these x1, x2, and x3, and now you can see why I called the last one x4. It just spaces out to have 4 rectangles, okay? And we'll do the same thing for the second rectangle. So the second rectangle's leftmost endpoint is actually at x1, and we can draw the line over from here. Now this one overestimates it quite a bit, at least more than the last one did. Now at x2, from x2 to x3, we have a third rectangle, x2. Okay, hang on. x2's endpoint's here. Our leftmost points here, and then we can draw our line over. This one's a little bit of an underestimate. I don't get quite all of the area of the curve on this shape. And then the last rectangle from x3 to x4 has the height at x3, and this one actually is quite a bit of an underestimate. Now, because we've got some underestimating and some overestimating going on, we kind of have the sense that maybe it'll balance out a little bit. It'll be close. And it really depends on the curve as to how close it is, right? There are some curves that we could have where we estimate the left endpoint and it's always an underestimate or it's always an overestimate. But the other thing is the more rectangles we have, the less of an over or underestimate we have as well. So I've drawn this with 4 rectangles just so that you can see the image of what's happening. I'm going to show you what happens on the computer a little bit later with what happens when you let the rectangles become much, much, much more, many, many more, whatever you would say. So this is just giving you a visual. So I want to show you what happens. Now, your book doesn't use this notation, but I think it's pretty handy. The last book that I used did. We're going to call this L of X. So that looks like an L sort of, script L. L for left, that's all it's for. And we're going to actually find out what is the area of these 4 rectangles. Well, you guys know how to find area. How do you find area of a rectangle? Say again for me. Length times width, right? So here's my rectangles. What can you tell me about this rectangle's length and width? Let's just do the very first one. Well, it kind of, I mean, we can call it length and width. It almost feels like a base and a height, the way they're sort of drawn in there. This base right here is whatever this distance is between x0 and x1, right? And what can you tell me about this distance compared to x1 to x2? They're the same. We created them to be the same, all right? So all of those distances along the bottom are the same, and we're going to call them delta x. You've seen that notation before. It just means the change in x, the difference between them. So this right here is the delta x that we're talking about. So for each of these, we're going to have the base, or the width, be delta x. And then the height, or the length, will be how tall the rectangle is. So if you take a look at this first one, how could I designate what that red dot is on top? What is that location? What is that value? It's f of x, right? It's just the height. It's the y value. So I didn't give this curve a name. That probably would have been a good idea. This is the curve y equal f of x. So if we're talking about this particular point right here, we're talking about the point f of x0. It's the height at the x value of 0, of x0. So if I take the base, which is delta x, times the height, which is f of x0, I would find the area of the first rectangle. But that's only one rectangle, and I have how many in my picture? 4. So the second rectangle, well, it has the same base, delta x. What's its height? F of x1. That's the second rectangle. Third rectangle, same base, delta x. What's its height? F of x2. Third rectangle, same base. What's its height? I'm sorry, fourth rectangle, same base. What's its height? F of x3. So what should you notice? Well, you should notice that the x4 value didn't get used as a height of any rectangle in this one, right? Because it isn't a leftmost endpoint of any of these rectangles. Now, the other thing that you should notice is what looks sort of like unnecessary in what we've written down. Do you see something here that looks a little bit redundant?
The repetition of delta x.
Yeah, that repetition of delta x. It's there on every single term, isn't it? So we learned something in algebra a long time ago called factoring. We're going to factor out that delta x because there's really no need to multiply it every single time. It would be much easier if we simply added all of those heights together and then multiplied them one time by delta x. Now in practice, this is what we're going to do. We're going to actually do this last step right here. I want to show you what this looks like in terms of something else you've seen though back in section 4.2. This should look like we're adding a whole bunch of things together, and what notation did we use when we did that? A summation notation. So another way to write this in practice is that we could write that, in fact, I'll write it the way your book does. They write the summation of the f of x sub I. In this case, the I is starting at 0 and is going to 3. Right? The subscript starts at 0, the last subscript is a 3. And then it gets multiplied by delta x. Your book puts the delta x at the end. I've had another book before that puts a delta x at the beginning. It really doesn't matter. But it gets multiplied by delta x when it's done. So this is what we're doing when we're finding leftmost endpoints. Is everybody okay with that one? Well, there's nothing special about the leftmost endpoints, right? Why don't we do it with right endpoints? That's another way of doing this. The image looks very much the same. We're drawing our lines in here. We're cutting it roughly in half, and in half again to make 4 rectangles. Trying to make rectangles look even. They're not really cooperating very well with me. And we're going to label them the same way that we did before: x0, x1, x2, x3, and x4. And of course the difference here, the distance between these, is delta x. The difference in what we're going to do, though, is that for each rectangle we're going to use the rightmost endpoint. So if we start with the first rectangle, and we don't have to start with the first one, but we will. The first rectangle, the rightmost endpoint is actually at x1 this time, right? So this is going to be the height of my rectangle over here, because it's the right side of that particular interval. In the middle here, the second rectangle's height would be at x2. Over here at the third rectangle, its height would be at x3. And on the fourth rectangle, its height would be at x4. And we get these 4 rectangles. Now we could write out all of the individual multiplication components of area as well, but we would end up getting the same kind of thing going on. We'll call this R of x for the right rectangles. Again, your book doesn't use this notation, but I think it's kind of handy. And eventually, they're all going to be multiplied by delta x, and I'm going to add up all the heights, just like on the last slide. Except that the 4 heights aren't the same 4 heights as they were before. What 4 heights do I have for the right rectangles? F of x1, f of x2, f of x3, and f of x4. And again, in practice, that's actually how we're going to work this particular problem. In terms of notation, you will also see this written from I equal, in this case, 1 to 4, right, of f of x sub I times delta x. So we're using the right endpoints to be the heights of the rectangle. Now we could really use any point between the left endpoint and the right endpoint and do this. There's nothing special about those points, except that they're easy to identify. That's really the thing that's special about them. There's one more point that's fairly easy to identify, and what would that be? You guys already know it from your notes. What's it say? The midpoint. That is the point halfway between the left and the right side point. And for many functions, again, not for all, but for many functions, this one does a really good job of balancing out the overestimate and the underestimate without having to increase the number of rectangles that we're looking at. So taking a look at this one, we're going to start at the leftmost point to the rightmost point. Again, cut the graph in half and then into fourths. And these are the points x0, x1, x2, x3, and x4. And I'm just going to mark them in red along the bottom with a point that looks like it's about halfway in between. And then I'm going to go up to the top and I'm going to plot that point on the curve. All right, so those green points now are the midpoints taken along the x-axis on the bottom and gone straight up. So it is important to realize that what you're about to do is going to kind of look like you've created 8 rectangles, but you didn't. You still only have 4 rectangles here. The width of these rectangles is still delta x, right? The difference here is still delta x. It's just that when we do this, we're going to end up sort of overestimating, and it's particularly for this function, overestimating and underestimating on the graph at the same time. Okay? So over here I'm cutting through the middle. Here, again, it looks like I'm cutting through the middle on each of these. So on this particular function, as it's created, it in each of the intervals appears to overestimate and underestimate a little bit, and thus sort of balance out some of the error in what's going on. Now, I want to avoid giving names to these little red marks. I don't want to call them x sub anything else's. That's just not real helpful in this particular case because we're going to get notation that's going to be rather messy. But the process is the same thing. We're going to use the height of that midpoint We're going to use the width of the original rectangles, and we're going to add those heights together and then multiply by the width. Is everybody good with it? Now, if you can imagine, if we were to let these rectangles become more, that is, there are more rectangles, we would end up with less and or more overlaps, but they would be much, much smaller. We'd have a whole bunch of them, but they'd be very, very tiny. And I'll show you a picture of that later, but I want to do a problem with you that actually goes through this process. And again, we're going to do it with n equal to 4. You've got some in your book. I don't think they're all n equal 4. Some of them have different values. You don't have to draw a picture for these. However, it might very well be helpful to at least draw a number line to talk about how you're subdividing the interval. So, for the sake of argument here, I am going to draw a picture, but the number line is the part that's going to be most helpful in our discussion. So I'm going to make the number line look a little bit longer than maybe I normally would have down here, because I'm trying to take this interval and divide it into 4 pieces. So I'm going to go over here from 0 to 2. This is the interval they're giving me, right? From 0 to 2. And if you weren't sure what the graph looked like, you could graph it. This is a shape of a what? It's a parabola. Do you know the y-axis or the y-intercept where it hits the y-axis? It's at 5. So over here at 5, we have the y-intercept. Let's do it in black. And if we find the y value when x is equal to 2, what happens when I plug the number 2 into this equation? 2 times 2 squared plus 5. What do you get? We get what? Is it 13? 13. Okay, so over here we're going to have 13 then, at a height of 2. And it's a parabola shape, so it looks something like this. All right, so we're going to make 4 rectangles, so we need to divide our interval down here in half, which means what location am I at right now? 1. And then I'm going to be in halves again, which means these locations are at what?
0.5 to 1.5.
Yes, and you can use decimals or fractions, whatever you feel comfortable with. 0.5 and 1.5 is what Blaine said, so that's what we'll go with. All right, so I'll draw in the rectangles without heights. The heights will be different depending on which part of this problem I'm working on, but these are the rectangles that I'm working with, right? So this is actually an example where if we do the left rectangles, they're going to all be underestimates. Do you guys see that? Every single one of them. And if I do the right rectangles, they're going to all be overestimates. The last one not quite, or this first one 0 to 0.5, not quite as much, but it's still going to be an overestimate. And if I do the midpoint, it's somehow going to be balancing things out on this particular one. Now, your book has these going in, I use the exact same directions at the top just so you'd be aware of them. They're going from left to midpoint to right, whereas when I was describing them to you before, I did it in a different order. So we'll go in the order that they have. We're going to do the left endpoints first, L of x. All right, so come down here and take a look. What are the width of every rectangle? Yes, that delta x down here is what? 0.5. So every single problem I do with this equation on parts A, B, and C have delta x equal to 0.5. Now, if I had 8 rectangles in this interval, I wouldn't have 0.5. I'd have to change that. Okay? But on this problem, we have delta x equal to 0.5. And then I need 4 heights because there are 4 rectangles. And if I'm doing the leftmost points on this interval, what are my 4 heights that I'm going to be using? The x values for them. 0, 0.5, 1, and 1.5, right? I'm going to use the 4 of those particular points. Now, be careful. This is the function value at 0, not 0. I don't want you to get a little carried away there and miss that piece. I want the function value at 0.5, the function value or the y value at 1, and then the function or the y value at 1.5. Now, we can enter these by hand. This is not a terribly complicated equation, agreed? It really isn't. But you also have wonderful table features if it were complicated. So let's practice that just to remind yourself how that works. If you grab your calculator, you put the original equation, 2x squared plus 5, and put that into y1 in your calculator. And then you can go into the table, and you can enter 0, 0.5, 1, and 1.5, and it will spit out for you all four y values, you know, not at the same time, but very quickly anyway. So this is 0.5. What is the first function value? What is the first what is f of 0? That one's 5. Okay, what happens when you put in 0.5? We get 5.5. How about 1? 7. And 1.5? 9.5. And then you're going to add them together and multiply by 1/2 or divide by 2. Yeah. All right, so what do you get for the left sum? What is it? 27, and then did you also multiply by the 1/2 already? Not yet? 13.5. So this, I'll write it down that you guys said that. So you had a 27 for the sum, and then when you multiply by 1/2, you get 13.5. So your approximation using left endpoints for this area is 13.5. Is that an overestimate or an underestimate? This is an underestimate. You should be able to see that visually by if you actually drew in these heights, that this one definitely underestimates this particular equation. Doesn't always underestimate, but on this equation it did. All right, so if we're going in order A, B, C, B is the next one, and it's a midpoint. We'll call it M of x. I didn't give it a name before now, but we'll use M of x. It's the same width, right? Yes, still the same width, 0.5. The function values, however, are not any of these numbers that are listed, are they? No. And they're not hard to find because these are actually pretty friendly values. What would be the first midpoint? 0.25. And the second one? 0.75. And then 1.25, and then 1.75. And I hope you're thinking about money because that's what I'm thinking about when I'm doing it. Coins and things like that. So we're going to find f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. And I really am modeling what I want you to write down. Your calculators, some of them, will do these sums for you very quick and easy, and it's great for you to check with that. But I want to see that you understand how we're finding them too. And this notation, this work that I'm modeling for you is exactly what shows me that you understand where these numbers are coming from and how you're using them. So you're going to plug each of those into your table. Your table will find for you the y value, and these are actually a little bit longer in terms of decimal expansions. What do you get at f of 0.25? 5.125. How about f of 0.75? 6.125. How about at 1.25? 8.125. And the last one at 1.75? 11.125. All right, so if we add all these together, and then we multiply by 1/2, what is this estimate? 15.25. We expected it to be a little bit more, right? If you actually drew these in, you're going to find that on half of the rectangle it's an overestimate, and half of the rectangle it's an underestimate. So we're not consistently underestimating when we're using the midpoint on this particular function. Last thing to find on this one then is the right endpoints. So, oops. We're going to do r of x. Same width, 0.5 for our rectangles. But the four heights that we're going to use are what? 0.5, 1, 1.5, and 2. We're using the rightmost endpoints on this one. So I'm going to do f of 0.5, f of 1, f of 1.5, and f of 2. And if you will notice, 3 of those 4 you've already found. If you're aware, you don't have to enter them again. 0.5 we found was 5.5. 1 we found was 7. 1.5 was 9.5. I do need to know f of 2. What was f of 2?
13.
It was 13? All right. So you're going to add those together and then multiply by 1/2 or divide by 2. And what do you get for your right sum? 17.5. And is this an overestimate or an underestimate from this picture? It is an overestimate. If I use the rightmost endpoint, I am overestimating every single area along that curve with that rectangle. Okay, any questions on this? All right.
If n would have been a different number, would you just have a different number of rectangles?
Yes, if n had been, let's say, 6, then you couldn't just half things and half them again, right? You'd have to half them and third them or something like that. But yes, you would just have to take the number line. And if it didn't start from 0 and go to 2, that'd be okay too, right? Like if it started at 1 and went to 5, right? Your numbers would be along the bottom would be different. That's why I think drawing at least the number line is helpful to make the claim of how I'm going to get those particular intervals. It's a helpful step to see it. Okay. Any other questions? All right.